Hello again. In this lecture, we'll be turning our attention to the intricacies of array dimensionality and introduce the squeeze function. Let's get coding. As always, we'll begin by defining the variable we intend to use for this video. Once again, this is a matrix, so we'll call it matrix D to avoid confusing it with the previous ones. Just to make sure we've done this properly, we also display it on the screen. Great. Next, we're going to use the type function to check on the first element of the matrix. To do this, we write type, and within the parentheses, we add the name of the variable, followed by 0, 0 between square brackets. The output reads numpy.int32. Hence, Python recognizes this as a single numerical value. We can also print it out to make sure that's the case. The output is just a 1, standing for one value. So, everything seems fine for now. Now that you're familiar with slicing, let's call the type function and substitute the second index with the slice from 0 to 1. As you know, this will only include the first element of the first column of the array, so the output should remain the same, right? Somewhat surprisingly, that's not the case. The output states that the variable is now an array, rather than a simple number. Let's once again print it out and comment on the outcome. After we've run the print function, we now see that the numeric value is surrounded by squared brackets, indicating it's an array. This is quite thought-provoking, because even though it's essentially the same numerical value, its type changes depending on our syntax. Let's repeat this, but this time we'll also change the other index from 0 to the interval from 0 to 1. Once again, the type is an int array. However, when we print it, we now see two square brackets on each side of the number. It seems like the new syntax results in a two-dimensional array. To make sure that's the case, we can print the shapes of the variable with the three different syntaxes. The one with two fixed indices is represented by empty parentheses, which means it has no shape. Hence, it's not even an array. Of course, this makes sense because the output of the type function stated this was a numeric value rather than an array. Therefore, using specific indices such as the integer 0 results in a scalar output. Next up, we see a 1 followed by a comma placed in parentheses. This indicates that we have an array of dimensions 1, so essentially, a vector. The last line shows a shape of 1 by 1. Thus, the last version results in a 2D array, even though it contains a single number. Therefore, the third slice corresponds not to a vector, but a matrix containing a single value. So, if all three notations contain the same numeric value, what difference does it make whether we're storing it as a scalar, vector, or matrix? Well, it matters because certain functions or methods can only be executed with inputs of a fixed size. So it's important to be consistent when working with arrays. So to avoid such potential confusion, we like to rely on the squeeze method. It removes all the unnecessary dimensions of an array. In other words, instead of displaying a 2D array holding a single numeric value as a matrix, the method gets rid of all excess dimensions. To understand this, let's just copy the notation which resulted in a 2D array in a new cell. Then add .squeeze parentheses at the end of the line and run the cell. The output reads array1 because the method always returns int arrays. To be more precise, when we squeeze an array along all its axes, as is the default, we get a single numeric value. However, this output is a 0D array rather than a scalar. To verify this, we'll need to check its type and shape. To examine the former, we call the type function which confirms it as an int array. Then, on a new line, we can display the shape attribute and see an empty set of parentheses. This indicates the squeezed array has no shape, making it a 0D array. However, if we print the squeezed array, we'd get a simple 1 as an output, which is the value that will be actually used in further calculations. This is perfect because it gives us the consistency we desired. Splendid! It's also good to know that NumPy contains an equivalent function with the same name. In a new cell, write np.squeeze, and in the parentheses, add the notation with the 2D output. The result is equivalent to what we got with the method. So it's up to you to decide which one you prefer. Superb! We mentioned that the squeeze method helps our outputs remain consistent. So let's see how uniform the results can be. In a new cell, we can copy the code we wrote to compare the shapes of the three similar notations. However, now we'll call the squeeze method for each slice. Be careful here. We want to insert .squeeze before shape because the latter is an attribute rather than a method. After adding it to every line of the code, we run the cell. We see that the output of each one is an empty set of parentheses. As we stated earlier, this means that all the outputs of the squeeze methods were scalars, so the results are equivalent. In conclusion, it is fair to say that as long as we apply the squeeze method or function, we can use any slicing variation to get the same chunk of data. All right, now that you know how to work with arrays, you're ready to move on to the next section of the course, where we will examine a new feature of NumPy, generating random data. As you gain more practice in using this tool, you will see why it can be so useful for creating tests and filling missing values. Thanks for watching.